Hey guys, welcome in this new sudden video. I was working and preparing a new tutorial for you guys about the DC-DC converter, where we will use a digital potentiometer to control the V out of the DC-DC converter. However, suddenly I have found some interesting things to make a new tutorial about, or how to control the potentiometer. So here we have two potentiometers, both of them from microchip. Okay, they are MCP4141, this on the left, which is a single potentiometer, and the one on the right is 4241, which is a double or dual potentiometers. Both of them 100K, but there are some difference between these two, which we can directly control them using an Arduino hardware SPI. Because this potentiometer got only a single line or single pin that control the read and write to and from the master. However, this one has two pins, one for the read, one for the write, or one for in, one for out, which is the master in slave out and master out slave in. However, this one is only pin and we need to multiplex it, so we need to see how to control these potentiometers, how to set the values, and then we will continue with the DC converter tutorial. Without further ado, let's get started with this new tutorial. Okay, guys, so here we will work with two potentiometers, two digital potentiometers, both from microchip. They are MCP family. One is 4141, which is a single potentiometer. Another one is 4241 potentiometer, which is a dual potentiometer. So this one is a single, this is a dual. Okay, so both of them, they are 7-bit resistors, which means we have 128 to 129 steps, as I highlighted here. Both of them 100K. Both of them SPI interfaces with them, with the master or with the microcontroller, and these are the parameters of the SPI, which is the frequency should be 10 megahertz, mode 0. What else? Shutdown, terminal control, TC. These all not really important to us. Working with the quite wide range of voltages from 2.7 until 5.5 volt, which is good to go with Arduino. Here are the packages we are working on. This is the 4141 potentiometer, which, as it says, a single one. Okay, this is the first one. The second one is MCP4241, which is a dual potentiometers. Okay, I'm working on this SOIC or TSSOP package, which is 14 pin, and the first one or the other one is 8 pins. So if you see, guys, here from the package, the main difference between them is you see here is the chip select, clock, and the data. If you see the data, we have two pins of data, which is the input and output, SDI, SDO, serial data in, serial data out. Both of them, they are multiplexed on the same pin. Okay, this one where they will link to the MCU or to the Arduino, we need to link them to the master in slave MISO, MOSI. Here we have a multiplex signal, so later we will learn how to play with this. However, on this type of resistor, our data signal, they're separated. So if you can see here, we have SDI, serial data in, and serial data out on pin 13. They are separated. So I can say this is like straightforward to be driven with the SPI. But here we might have some tricky way to drive it. So that's why I have come with this tutorial or video. Okay, so first I will go with the dual resistor first, because straightforward, just to make you familiarize with with a way to talk to the resistor and how we set the resistance for this type of resistors or digital potentiometers. Then when we come here, because we need to play with a bit bank and also like special commands, I can say, or functions to drive these type of potentiometers that you use multiplex data. Okay, so here are our two potentiometers. I highlighted in yellow. So number of what, as you can see here, 4141, there are only one potentiometer. Here we have two potentiometers. Both the SPI, both they have EEPROM. Okay, both of them we can use them to save them. I mean our data in, because we have some others they are just RAM, not ROM. Wiper lock, yes, we can lock the wiper, but I can't see why we need it, but it's there. And both of them, they support non-volatile wiper. Okay, this one kind of important because we will see later we might need this function for our safety, or not our safety, actually, to make the project safe to power up, because sometimes when it's powered up, most of the other devices, for example, you see the first and the second one, they are mid-scale. Mid-scales mean when they're power on, this is power on resistor, power on reset wiper setting. I mean, when they recycle the power on the device, always the wiper will be in the middle scale, which is really dangerous, especially if, let's say, you set it to a power supply, high voltage, high output power supply, or you set it to like a sound amplifier, that whenever you turn on, always go to the mid scale, which is kind of not, how can I say, not accepted. You need to go, when you just reset your system, need to go to, let's say, 0, or should be at the minimum output. Or maybe you can set the setting like, okay, when it's power on, what is the resistance you want to be, or what's the output, the desired output should be. So that's why this is very important to have a non-volatile wiper. So we can set it, let's say, when it's power on, the wiper should be at this level and the output should be at this level, that it's suit our application. Operation range, I mean the full resistance, it's we got the 5, 10, 50, 100, and ours is 100K. Wiper resistor 75. Okay, a number of steps, both of them 129, and the operating voltage from 2.7 to 5.5. Since we are using Arduino, so 5.5 more than enough, because we will supply 5 volt to them. Let's check the rest. Okay, so here it shows you the resistance. As he said, we have the 100K, so minimum, maximum, the tolerance will be from 80 to 120K. Resolution will be 129 resolution, so we just divide the so if we want to calculate the step resistance, we divide the full maximum or scale, which is 100K, divided by 129. So if we come to here, we change to standard, so we have 100K, 100,000 divide by 129, so about 700 ohm per step. Okay, 700 ohm per step. Are we calculate correctly? Yes, it's 100K divided by, yep. So because here also it mentions you the maximum resistance RAB, which is 100K divided by 28, which is 120 or 29. Not that different, I believe. Let's recalculate again. So 100,000 divided by 128. Yeah, 780. No, not that different. Previously we got 770. What else? Maximum current can drive through the potentiometer is about 2.5 milliamp. So this is good to be noticed. And what else? Okay, so here are the pins or the signals. They are on our potentiometer. So we have chip select. We use it to select the because we might, since we use SPI, we might have more than one chip on the SPI bus. So we use the chip select to select the the chip or the potentiometer that we are working on. Serial data in, again from the name, is accepting or reading the serial from the master. Then we have somewhere serial data out, that will be output data to the master. And we have SDIO, which is the multiplexing of input and output, and this is where will be a bit tricky to drive, and we will be discuss about this in the second part of this video. In this video we will usually use the standard one, which is the separated SDI SDO. What else? Here's important table, but later I believe there's more detailed one, but this is important one. We have a memory address. These are the memories that we can work with. We can play with the volatile wiper 0, volatile wiper 1. This means these wipers, when we set them, then we reset the device, all the setting will be gone. But we can set it for the real-time control. Then we have non-volatile wiper 0, wiper 1, which we will use them to set the memory of the wiper. So when we reset the device, we'll be recall these settings that we set inside the EEPROM, so they won't be changed. Then we have the T-con register, sorry. This is the terminal control registers. We will learn later how what is it and how to control it. And also we have the status register. They're both RAM. And we have about 1, 2, 3, 4, 5, 6, 7, 8. We have 10 bytes of EEPROM, so we can use them for whatever we want to do. Let's move forward. We will have a more detailed one. Let's see. Here is the communication or the wiring between the MCP and the MCU. Again, if we have the SDI and SDO, they are separated, so we can straightforward connect them to the host or to the MCU straightforward directly using the normal SPI wiring, which is MISO, MOSI. But if we have the SDIO multiplex in a single signal, as in 4141 chipset, then we might need to do some thing like this to drive the bin, which we will talk about this later. Okay. Here is the important thing, guys. So if you see here in the table, you previously remember we have a memory address that we discussed about previously. So here are the command that we can do to the memory address. We can read, write, increment and decrement to the memory addresses. Okay, so these are important. Also later we will play with this a lot. Okay, so here is the command that we use it to talk to the potentiometer. So this command is a combination of 8 bits, and these 8 bits, they are divided into 3 groups. We have the memory address, okay, and then we have the command bits, then we have data bits. Okay, the command bit, there are 8 command bits. They divide into 3 groups: memory, command, and data. Memory, the one we discussed the first time up there. Command, they are here. These are the command, whether read, write, increment, decrement, and the data is the data when we need to read. When we need to write it to the designated memory address. So here are again the detailed one, as we said. So here I can say it's not the completed one, but I can say give more clear picture of what we can do. So for example, 00 is the wipers, or the first potentiometer wiper, which is volatile. 00, first potentiometer wiper, volatile, and we can do write data, we can read, we can increment, we can decrement. Okay, so if we want to send, let's say, we want to write data to the volatile wiper 0, we need to send 00 and the write data. So the write data will be 00 also, then our data. Okay, so 0000 and our data.
Okay, so if you can see here, 0, 0, 0, 0, and NN is representing the data. And so goes to the second one, which is the volatile wiper 1 for the second potentiometer. If you want to read or write, we should send this memory address first, then we concatenate whether we want to do read, write, increment, or decrement, and we send it along with the data to the chip to perform the function. And so on and so forth. For example, here number 3, or the value of the memory address 3 representing the non-volatile wiper 1, then we can do read, write, and etc. And if you can see here, this is for the tcon, volatile tcon, we can do read, write. And for the status register, which is byte number 5, we can perform only read. We cannot modify it, you just say the status, because the status of the chip itself, it will return to us what is the current status of that of the chip. And here we have our memory address, we have EEPROM storage, which is about 10 as we said. So here are the addresses, and we can do read and write to them. So if you can see here, the increment, decrement will be reserved only for the wipers, okay, for the wiper, and exactly to be more exact is for the volatile wipers only, not for non-volatile. These are not supported, okay. So mostly will be only for the increment, decrement will be for the volatile wipers, but read and write will be most of the rest of the memory location support this read write, except the status register support read only. So this is important. We will use it a lot when we drive our code. Remember that. Table number 7-2. What else we need to talk about? Yeah, so this is how we will construct our command. This all we'll talk about in our coding. I guess that's it. Okay, let's go back here, guys. I just want to highlight something to you. When we use the potentiometer, let's say we use the first potentiometer number 1, because here's the potentiometer number 0, this is potentiometer number 1. Either one, when we use them, first we can exceed the current, the current being mentioned in the data sheet. The maximum current is 2.5 milliamp. The second thing, the voltage, it shouldn't be you see the input voltage at this terminal, it shouldn't be exceed the supplied voltage, okay, the VDD. So if you want to apply any voltage to this resistor, for example, to drive any load, the voltage shouldn't exceed the VDD voltage, which is a 5 volt or 2.7 up to 5 volt, okay? And the current should not be exceeded 2.5 milliamp. So these are the most important thing that we need to consider without damaging our chip, okay? So let me highlight this one also, it's kind of important. Again, the voltage shouldn't be exceed the VDD, and the current shouldn't be exceed 2.5 milliamp. Okay, guys. So now talk about the wiring. So here I have draft a very fast wiring diagram. So we will use this for our prototyping and also testing. So here is the MCP chipset. For sure, guys, it's not like one line. It should be in a U sequence, but here I just put it in one line just because it's easy to be implemented. Anyway, so the pin number 1 of the MCP, let me open the, okay, yeah, let me open the data sheet. Yep, let's put it here. Yep. Okay, so pin number 1 of the MCP, which is the chip select, okay, the chip select will go to number 10 of the Arduino. I will use Arduino Uno. Pin number 2 of the MCB, which is the clock, go to pin number 13. Pin number 3, which is the SDI, will go to number 11, MOSI, master out slave in the Arduino. 4 and 5, pin number 4 and 5, they go to the ground. Okay, pin number 6, which is the wiper here, the wiper, the middle one, will go to the multimeter, so we can measure the output, because here we will use the potentiometer as a voltage divider. That's why we connect this pin number 5 to the ground, and we will connect number 7 to 5 volts. Okay, number 7 to 5 volts, so we will use it as a potentiometer. So when we change the wiper position, we can read the output voltage from the wiper. So that's why the wiper will go to the multimeter. Then we continue with 7, go to the 5 volt. 8 also go to the 5 volt. 8 is the another terminal of the first potentiometer. Number 9 again go to the multimeter, so we can measure both resistance output. Number 10 ground again. Number 10 is the second terminal of the potentiometer. Number 11 and 12, we are not using it. The right protection, the wiper protection or the right protection are the shutdown. We just don't use them for time being, because we don't have any protection. We just want to full access to all the registers, so we just keep them without connected to anywhere. Pin number 13, pin number SDO, will be connected to MISO. Pin number 12 on the Arduino, and 14 VDD connected to 5 volts. Okay guys, so we will follow this wiring to implement it on our breadboard, and we will proceed with our coding. So enough talking about the data sheet, and let's dive into the coding. So first, allow me to paste the IO's communication between the chip and the Arduino Uno. So these are the wires we need to perform. Okay, again, this is on the left numbers, they are from the chipset, and the right one, they are going to the Arduino. Okay, okay, cool. So what next? First, since we're working with the SPI, so let me include the SPI library. So hash include what we are working on, SPI .h. Now we need to declare our chipset. Let's use is a constant. So we want be able to change it in the code. Constant integer chip select pin. For us, we are using pin number 10. What else? Let's declare the SPI settings. So we will declare an object named SPI settings. So this one we will use it later when we begin the transmission. We will call it we'll use the MCP settings. Sorry, this is the object that will be inherit the SPI settings parameter. So here we will declare the frequency is 1 megahertz. So will be 1 2 3 4 5 6. Okay, 6 zeros, mega, and will be MSP, most significant bit first. Yes, and the mode will be mode 0. SPI mode 0. Let's compile and check if everything is okay. Okay, cool. Everything looks good. So now, guys, if you remember to construct our code, or not code, the command. So we have 8-bit commands. Okay. So this 8-bit command consists of. Let me copy this from the data sheet. hold on. Let me paste it here. Okay, yeah, here's much better. So if you see, guys, we need the memory address, the first 4-bit memory address, then the command bit 2 and data bit. Okay, so what I will declare here, first I will start with the memory address. So here I will declare MCP MCP4241 memory address. Okay, so if you remember from the data sheet, let's go to memory address, Control F. Why it doesn't go to the memory addresses directly? Not really this. We have a nice table last time we saw here. Okay, so first I will declare these values. These are the memory addresses, okay, which is start from 0001. So let me put this one. Oh, it's okay, I can do it one by one. So first I will use the HDefine technique. So HDefine, we have volatile wiper for put potentiometer 0. Okay, this is the first one. So we have volatile for wiper for potentiometer 0. The value is 0, 0. So we will convert it to the binary here, which will be 0B1234, because we have 4 bits of the memory address. So this will be wiper for potentiometer 0, okay, which is volatile. Then let's copy this guy. What else we have? We have a volatile wiper for potentiometer 1. Sorry, here POT potentiometer 1. Let's give this space. This one I believe will be 1, isn't it? Yes, it will be 1. So the binary for that will be 0B0001. So this is exactly the same, but for potentiometer 1, the second one. I need to copy this guy, HDefine. Okay, now I will declare the non-volatile. Let me copy these guys. I guess will be faster if I do like this. So this one will be the non-volatile wiper put 0 and non-volatile put 1. Okay, cool. And this one will be 2. We just follow the sequence. So this one will be 2, and this guy will be 3. Yep. So this one will be the non-volatile for both 0 and non-volatile for both 1. Cool. Now what we need to define next we will work with a T-con, I believe. So non-volatile, yes, is a T-con register. So T-con is a volatile, so volatile underscore T-con terminal control register, and this guy will be 4. So 0B0 4 will be 100. Oh, sorry. Why there's a double B? Okay. So 0B1 0100. So this one will be the volatile T decon. Yep. Next, I believe, is the status register. So will be status underscore register, and this one will be 5. So the value will be 0B0101. Okay, this is number 5. So this is the status register. What next? Let's refer to the memory again. So after the status register, all of these, they are memories from 6 until F. Okay, so we need to define, I will just take the first and the last address, 6 and F. So I will declare the first address of EEPROM will be 6, so 0B 01106. This is the first EEPROM address. Then I will have the last. Let me copy this. So this will be the last EEPROM address, and will be FF is mean 4 1s 1 2 3 4. Okay, and this is the last. Okay, cool. Let's compile our code. So these guys are the memory addresses that we will access them to perform read, write, increment, decrement, etc. Okay, let's compile. Good, done. So now I will work with so I have MCP4241 command type. So the command type, we have 4 commands to be performed on these registers. Okay, so let me use hash. Oh, sorry, I will define them here. So hash define the command type. We have command underscore write. Okay, and the write will be 00 if I'm not mistaken. It's somewhere up here. Yes. So the write will be 00. Write will be 0B00. This is command write. Now I will have I'll follow the table. So 0001 is increment. So we have cmd underscore increment. So this will be 1. So 0B01. This is command increment. And then we have command decrement, then write, then read. Decrement and read. Okay, so we have command decrement. So decrement will be 2, so 0B10. This is 2. So this is command decrement. Then we have the last command type, which is read. Read is the third and the last command, which will be 0B11. This is number 3. So this is command read. Yep, that's good. Let's compile and check. Okay, good. Everything looks nice and hangadori. Good, guys. Up to here, we have defined all the variables or the thing that we need to use it later, which are the 2 groups here we have, the memory location and the command type. Okay. memory location, command type, then data later we will add on. So now we just need to combine them together and send them in sequence to the chip through the SPI to perform whatever we need to do. So now I will construct the what we call the SPI functions. So MCP 4241 SPI functions. Okay. So the first function will be to build the command type. Okay, to construct the string for the command. So this one we will use unsigned integer. Yes, please, because we will return the constructed command. We will call it build cmd. Okay, what do we need? We need the memory address, and also we need the command type. So we need unsigned integer, yes, memory address, and unsigned integer command type. Okay, and what we will do, we will first take the memory address and we will shift it to the left 4 times. Okay, because we have 4 bits, we shift it 4 times, so then we will have 4 spaces, 2 for the command, 2 for the data. Okay, so we shift this one 4 times. This is the important thing, guys. You need to focus here. Then we will OR it. We need to add the OR with the command type. Command type, but we need to shift it. We need to shift it 2 times. Okay, 2 times, because the last 2 will be the data. Okay, so we need to perform this logic operation, and we need to return this. Okay, so we need to return the memory address shifted left by 4 to give space for command type and data. Then we take the command type, shift it by 2 only, and concatenate it together using OR. Okay, so this is the first function that we will be used. Now I will drive or write the what they call the write function, SPI write function. So since we are writing, so we won't return anything, so the function will be void, no need to return anything. I will call it MCP write. Okay, so this MCP write, what it needs to be right, I mean, if I want to write to any of these what they call any of this memory location, I need to know which memory location I need to write to and what is the data. So I need this and I need this, because write, by write, it should the command type should always be 00. But in order to write, I need memory address and data. So to write, I need again unsigned integer, because all positive for sure. I need memory address again, is a local variable anyway, and I need another unsigned integer data or value that I want to type it or write it, I can say. Okay, so what to do here? First, let me add a comment. So since this is a write command, so the command type is always 0B00, okay, because it's a command type. Okay, so what we can do is, first we need to start the SPI. So begin the SPI transmission. How to start it? We use SPI dot begin transaction. Here we need the SPI settings. If you remember, guys, up there we use MCP settings, so we will replace this with MCP. Not sure if can he find it. Yes, MCP settings. Then here we already begin the transactions. Before we do any read or write, we need to handle the chip select. Okay, this chip select need to bring it down or bring it low, so we need to perform digital write. The pin, we will work with the chipset pin, and the value will be low. Okay, we bring it low first. Then what we can better here, we give some delay, so we make sure everything is being done correctly. So I will add a delay in microsecond. Let's say 10 mics should be enough. What else? Now I will start the transmission. So SPI on transfer. Okay, what I need to transfer? I need to transfer the command, which is the one consists of the memory address and the command write. Okay, so I need to call the function that build the command. Okay, build the command. But what I will send the memory address that is being assigned here from the function. So I will send the memory address. Okay, and what else? Since this is right, or before this, actually, this is a command. What is needed is memory address and the command type. So since it's right, so it will be always command write. So I will send it cmd underscore write here. This is the one. Okay, so I will send this to the command build, so it will return to me memory address shifted by 4 along with the command write shifted by 2, all to the left. Okay, then I'll give some time to the chip to digest the command, and I give it another delay, microsecond again, and this time I'll give it like 150 microseconds. Now I will send my data. Here I tell the chip that I need to write to that memory address. Now I need to send the value that to be written. Okay, so value to be written, again we use the SPI dot transfer the value. Okay, I send this value that's been assigned to this function. So now I will tell the chip to write this value to that memory address. Okay, cool. So after I finish, now we need to bring back high our chip select. Okay, because we finish with this command, pending the next, or waiting for the next command. So this one will be high. Okay, and what else? We need to end the transactions. So SPI dot end the transactions. Okay, let's compile. So I believe that's it, guys. This is the write function that we use it to write to the MCP potentiometer. Okay, cool, it's done. So now I will perform the read. Let me copy this, because the read is mostly same but just small different. Okay, no, I guess I will drive it again because it might be a bit confusing. Okay, never mind. So now we will write the MCP read function. So since it's read, it will need to return to us a value that's been read from the chip. So it will be unsigned integer. Yes. This one will be MCP. Let me make it seem like the other one. It will be MCP read. Okay, if I want to read, I need what? Only the memory address. Okay, why? Because the other command is always read, so I don't need it, and the data will be fetched from the chip, so I need only one variable here. Again, you unsigned integer 8. I need a memory address. Okay, what here? So again, since this is a read function, so the command type is always read will be 1 1, isn't it? Command will be 1 1. So always will be 0 0 0 0 0 B 1 1. Okay. Okay, cool. So again, we need to start the transition, the SPI transaction, and we bring this low, and all this need to copy the same. Okay, we need to start the transaction, bring it low, wait for a few microseconds. Then I will send. I will send this guy here, okay? But this time I will not send command write, I will send command read, yes. Just to tell the chip that I need to read from that memory address. Yes, I need to read. So now what I need to have is to read the value. So I have read integer, unsigned integer, value equal to SPI dot transfer. Since I want to read, so I can send any dummy value. In this case, let's say I'll just send 0x00 or 0b00, whatever. I just send any value that trigger the chip to send me the data back. And then at the end, I will close the transmission. Okay, bring the chipset high again and end the transmission, and don't forget to return the value. Okay, so this is the read function. Okay, let's compile. Hopefully everything is good. Okay, cool. So what we have else left? So we done the write, done the read. Now we have increment, decrement. Let's work on them. So here we have increment function. Increment, again, we don't return anything. We just ask or instruct the chip to increase by 1, increase the wiper by 1. So it will be void MCP increment. And what I need to send, since increment by 1, always increment by 1, so I don't need data, I need only the memory address that need to be increased. So unsigned integer 8 memory address. Yep. Again, here for increment, the command type will always increment, I guess, is a 1 0 0 1. So it will be 0B 0 1. This is always like this. So what I need to do again, the first few commands will be the same. I believe this all will be the same. So I need to start the transaction, bring it low, wait for a few milliseconds, a microsecond. Now here I don't need to send read. I will send command increment. Okay, this is to tell that I need to increment at that memory address. I just increase it by 1. Okay, that's it. Then after I increase it, then we just need to close the transmission or the transaction. Okay, so bring it high and the end transaction. Actually, guys, why we need to begin the transaction and end the transaction at every command? Because here we might have more than one chip connected to the same host, to the same MCU. Then we might need to talk to them at different time. So if we already begin the transmission with one, let's say chip A, and without closing it, we might not able to talk to another one. So it's always better to begin the transaction and close it after we finish talking to the chip. Okay, cool. Let's compile this function again and see if it's okay. So we will proceed with the last function. Looks okay, hopefully. Good. So the last function will be decrement function. Again, decrement is just to decrement us or instruct the chip to decrement the wiper without retaining anything. So it will be void again. So void MCP decrement. Okay, cool. And again, here I need only the memory address, so I'll copy this again because it will take the same like the previous one, but just will be decremented. So this one, I guess, yeah, I will take exactly the same from this, because just the difference is from increment to be decrement. So this command type will be 10. Let's confirm. Decrement will be 10. Yeah. Okay. So again, MCP start the transaction below this one. This one will be command decrement. To decrement at that memory address. This is high and end the transaction. That's good. So I believe that's it. Okay, so looks everything good. Now we can proceed with the rest of the code. Since I believe we finished most or all the function actually that we needed to talk and set the MCB chip. So now let's go to the setup function, setup, and we see what we need to add here. First, I will initiate the serial monitor, so we can bring any data to the serial to see what we are doing. So we need to have serial.begin. Baud rate will be 9600, should be it. What else? Yes, we need to begin the SPI. SPI begin also. What else? What else? We need to declare the mode for the chipset bin. Okay, so we need to declare the mode for the chipset bin. So we have bin mode chipset bin. Let's find it. Chipset bin. Yes, will be the mode will be output. What else? Let me think. I guess, guys, that's it in the setup. What else we can do? Just maybe bring something. Serial dot print line. We call it starting the MCP4241 testing. Okay, let's compile this guy. And now, once it's combined, let's go back to datasheet and we see what we can do. So I will follow the table, then I will check, oops, what is it? Then I follow the table, then I'll try to check the functions of every memory address. So for example, start with writing to the volatile memory of wiper 0, which is 00. Then we continue with the rest. So now if we want to change the wiper settings for potential 0, which are the volatile, so we need to do the following. We do something in the loop. Okay, so first here we write to the volatile wiper of potential 0. Okay, so we will write from 0 all the way to 1 to 8 to the maximum. Then what we will do is we will do the opposite, or we reverse it. So it will be 1 to 8, we go all the way down to 0. So how to do that? Again, need file for loop, for byte, let's say I equal to 0, and I is less than 129, less than the maximum, and I need to be increased by 1. Now what we need to do here, first let's print the I. So serial.print line, print the I, so we know what we are sending to the potentiometer. And now I want to write, so I will call the MCP write. Okay, I need the memory address. The memory address that I need to write to, if you remember here, we need to write to the volatile wiper 0. So volatile wiper 0 of this potentiometer. So I need to copy this guy. I need to write at this memory address. Okay, and the value, it should be following the I. Yep, that's it. Then we give it some time so we can measure it with the multimeter. So I have to add delay of maybe like 3 or 250 millis should be enough, and that's it. That's it. Now we will add another delay here. So before we start with the new loop, it's also 250. No, this one should be here, 250. Okay. So now we start with the loop. I will copy this because exactly the same, but just it's just that the I will be upside down. So the I will be 128, 128, and this one should be more than 0, or more than 0, more than or equal to 0, and I will be minus minus, and we send the I, and yep, I guess that's it. Yeah, and here also maybe let's add delay. So let's go back again. Well, we can see what is happening. So let's see, there's an issue. No. Okay, good. So it's compiled happily and everything good. So now guys, we are ready to upload our code to the Arduino and see how it functions. Okay
Guys, so here is our breadboard. It looks like messy, but believe me, I just follow the wiring diagram that I shared with you earlier. This is our target, the MCP chip. This is Arduino Uno. I already pre-wired it according to the iOS diagram I showed you previously. And here are our terminals. I believe this is the first potentiometer. This is the second potentiometer here. 1, 2, and this is the ground. And here we go. So now if I connect this to the computer, now I believe I can upload the code and we can read the readings on the multimeters.
Okay, so now let me upload it to our target, which is Arduino on port 11, and here we go. Yeah, so I will power up my multimeter, and oh yeah, because you see now when I power up the multimeter is I connected to the second potentiometer. Second potentiometer defaults been set to 2.55. I mean set to the middle, so the middle will give me like 2.5 because half of the 5 volt. So now I will move it to the second one that it should give me the readings. Here we go. So you see now is counting down all the way, should go to the 1 volt, then later we'll go up to 5 volt again. Here we go. So if you see now in the serial monitor, go like 70 something, and go down to 60, then 50, and the voltage readings also is dropping. When go all the way to 0 in the serial monitor, the voltage should go to 0 as well. There we go. Now it will go up again. Oh, it should go up. Oh, why 2, 4? Okay, we might did something. I should be this. I more than or equals 0. This one shouldn't be 200. There's something wrong here, but this one's correct. Byte I. Is it because of this need to be integer, I believe? I'm not sure why. Okay, let's try. There we go. Now let's go up. Should be stopped until 128. Here we go. Now go down. Okay, good. Now when it is 0, should start increasing to 1 again, not Yep. Now looks correct. Okay, good. Now looks correct. Yeah. So the issue was this one should be integer. I'm not sure why. Although I believe this byte should be same, but it might be something wrong. Okay. Anyway, so if you start counting up, we can notice that the reading is increasing from 0 all the way to 5 volt, because again we set our potentiometer as a voltage divider. Then it will count down, then the reading should go down as well. Here we go. So it's coming down and our reading is dropping. So again, this is only for potentiometer number 0, or the first potentiometer. So now if I need to test the other one, I need to change this to number 1. Okay, and this one also to potentiometer number 1, because if you remember here, my first memory address was 0, which is the first volatile wiper for put 0. Now I'm testing the second volatile wiper for put 1. Okay, so I change here in the while loop. I change the memory address to the first to put number 1, volatile wiper put number 1. I also have volatile number put number 1. So let's upload this guy. And now what we expect, guys, this potentiometer should stop counting, because now we're sending to the second potentiometer. So this one should be maintained at the last readings, And yep, here we go. So it's stop. And when we move the multimeter to the second potentiometer, then we can see the second potentiometer start to count again. There we go. Okay. So here we have done with that. Where is the data sheet? Yeah. Okay, so good. Okay, cool. So we can see is counting up, now counting down. So now we have tested the wiper writing, okay, the non-volatile writing data. So now we will try the increments. Okay, so next we will try to play with the increment. Okay guys, so we have reached to this level so far where we send the data to the wipers, the volatile wipers, using a counter. Or this is how we send any data to the volatile wipers of potential 1 and potential 2. Now we will test the increments, MCP increment decrement function, instead of we send an exact data. Okay, so we will, this is the decrement one, so we start with the increment. So I will comment this. Instead, I will use on the function called MCP increment. Yep, I'll use MCP in increment. And if you notice here, guys, for the increment, it will always increment by 1. So I just need to send the memory address, which is volatile boot 1, since we already connected to boot 1. So I'll start with the boot 1. And that's it. So now for the decrement, I will comment this guy, and I will call MCP decrement. Hello, can you find it? Oh, CP, MPC decrement. And this one will be volatile boot 1. Yep. So that's it. So these guys will increase or decrease the wiper by 1 whenever we call this function. Okay. Yep. Let's send it to the Arduino, and we send output. We should see almost exactly the same output. Okay. Here we go. Okay, good. So it's already been uploaded. I have opened the second camera. Let me turn on my multimeter. Here we go. And here we go. So now I believe we are increasing. But if you notice here, it reached to 5.12 and stop here, because when it's increasing, it's already been preset. But now when we go down, the value should go down. Okay, because we reached the limit already. Here we go. Okay, we will talk about this later in this tutorial. Okay, here we go. So it's go down, because this one was increasing based on the previous reading. I said the previous reading almost near to the 4 or 5. So it's keep increasing. It doesn't know actually what is the previous value. Just keep increase. So that's why when it reaches to the maximum, it's like there. Now should be okay. When it go down, reach to 0. Here we should expect some 0. Then it will go up again. Here we go. So now everything are working just fine. Okay, so what we can do now is we check the increment decrement for potentiometer number 0, or the first potentiometer. So we change this to 0, change this to 0, then we upload again. Now we should see the current potentiometer number 1 should be stopped at whatever its value, then it's increasing or decreasing the second potentiometer. Okay, there we go. It's compiling and it should be uploading now. Yep. Okay, here we go. So you see now the first potentiometer number 1 is stopped at 4.0. Now if I move to the first one, here we go. We should see it now increasing or decreasing. Again, now you see, guys, when it's increasing here in the potential on the serial monitor, the potentiometer is showing 5.1 only. Why? Because the previous reading was already high, near to 128. So then you keep add up, but it maintains at this value because it doesn't have more than 128, although we keep increasing. But when reach to 128, then we decrease it, then we should see it, here we go, is dropped down. So that makes sense actually. Okay, cool. So let us go down to 0 just to confirm everything is okay. Then we see what to do next. Okay, for T something now. Can do it. Almost there. There we go. Almost reached 0, and our multimeter shows 0 now. Should go up again. Voila. That's nice. I'm happy with the progress so far. So we have done the volatile wiper 0. We done the right increment, decrement. And for volatile 1, we have done again right increment, decrement. So next we will work with the read data. Okay, we read the current volatile wiper position. Then we will continue from there. Okay, so now we have reached to the part where we will try to read the volatile wiper. Okay, so to read the volatile wiper, we can make it inside the, actually we can, not cannot, but it will be so fast for us to notice any changes. So I will comment this guy here, and I will delay, just leave it there, and I comment this. So I will do it somewhere here, okay, because this will be very fast, so it's good for us to perform it here. So what I will do is I will call the library that will print the, or not print, so it read the memory location of the volatile wiper 0, volatile wiper 1. Anyway, so what I will do is the library, or sorry, the function called MCP read. Okay, MCP read and the memory address again. What I want to read, I want to read the volatile port 0, volatile port 0. Okay, what else I want to read? I want to read the volatile port 1. Okay, I want to see what are these wipers are set to. So now we need to print them out, but before I print them, let's go serial.print. So I will print some message to show us what we are looking at. So this is potentiometer 0 volatile wiper. Okay. And again we have serial print line here, a serial print line. We print out the red value of these guys here. Yep, exactly. So I will just copy this, paste it here. So this one will be boot 1. This one also should be 1. Okay, guys, so now I will run my code, and we should see what are the value that's been set to these guys. Okay, there we go. So I'm uploading it to the board, and let's see our results. Class has no member print. Oh, sorry, this is T print line, print line. Okay, sorry, now should be okay. I wonder why I highlighted the print without T is already highlighted in orange. Looks like it's a reserved keyword, but it's not. It's weird, this IDE compiler. Okay, it's done. So now we go to here, and here we go. So if you notice, guy, the wiper for potentiometer 0 is 106, but wiper for potential 1 is 101. This one is directly after we how can I say, after we done the testing with the increment, decrement, and also wiper, or what they call MCP write, that we write to the wiper without hard reset. Okay, that's why we can see this result. This is the last time we modify the write. Then we stop at these numbers. So now if I hard reset the board, I mean I disconnect the power, I connect again, these number will be reset to the default value. Okay, I will reset now. There we go. I disconnect the cable. Now I connect back again. Now it should reboot again, and here we go. You see now it's reset. Why? Because this is a volatile, guys. So the volatile, although we set it previously to see 106, 101, it's reset to 64. 64, this is the default value, I can say, that's been stored in the EEPROM and is located in the non-volatile wiper. So non-volatile wiper is being set to 64, okay? So the non-volatile wiper memory location, these guys, the non-volatile wiper put 0, put 1, it's being set to 64. So if we didn't set them using the volatile, then the chip, when it's powered up, okay, when it's powered up, it will immediately load the non-volatile readings, okay? So to prove that, let me read the non-volatile. For example, here I will copy these. So these are the volatile. Let's do here. Read the volatile wipers. Now I will read the non-volatile wipers. So read the non-volatile wipers. So this one will be potential for volatile, will be non-volatile wipers. Here also will be non-volatile wipers. This one will be, I guess, is N. Is it N underscore? NV, oh no, just NV, I guess, yeah. Non-volatile. Yep, correct, non-volatile. So now I'm reading non-volatile, non-volatile, and these are the non-volatile. So now, if I read these guys, I should see the same. I should see the same reading, 64. Let's see. Here we go, is done and is reading. Yep, you see now, this is the non-volatile 64 and the volatile now 64. Why? Because when we power up the chip and we didn't touch the volatile wiper, it will read the non-volatile and update the volatile. Okay, so now I will try to manipulate the volatile. So now I will write or change the data to the volatile wipers. Volatile, guys, will be a real-time update to the monitor, to the potentiometer. Okay, so to write to the what they call the volatile, so I'll use MCP write. Memory address will be volatile. For example, the first one I want to set it to 10, and the second one I will set it to, let's say, 100, yeah, why not? Okay, so now I have modified the volatile. So let's see what will happen now. Okay, good. So now we go to the CL monitor. Yep, here we go. So if you see, guys, oh, by the way, if you see here, the volatile 0 become 100 and this one becomes 64 for volatile. but actually we already set them to different readings here because we don't give space to them to how can I say, to get the data reach to the target, then we immediately write another one. So it's good to, oh sorry, no, not only we need the delay, but we haven't changed these readings, so this one should be 1, sorry. And also it's good practice to add delay here. Delay maybe 500 milliseconds or 200, I guess should be okay. If not, later we will change. Better also, yeah, to give some delay here. And yeah, this one being changed. Okay, let's hit again. Sorry, that was a mistake. Okay, uploading and done. So now change to the CL monitor and let's see the result. Here we go. So now potentiometer 0, volatile wiper we set to 10, the potentiometer wiper 1 we set to 100. Here we go, here it is. But the non-volatile, it's equal to 64 still, because this one's a non-volatile being stored there. If we didn't change the volatile, when we reset the chip, it will automatically read the non-volatile, then we'll update the volatile. Okay, so now for example, I don't want to write anymore. Okay, you see, although I didn't write now, then I upload again. The reading of 10 and 100 will be maintained. Okay, because the volatile is still there, the chip haven't been recycled yet, it's still in the RAM, and this RAM it will lose the data only if we lost the power. So now I should maintain, here we go, maintain the 10 and 100 until I reset the power from the chip. So now I will disconnect it. Here we go, I disconnect the power, I will reconnect again. So now the reading should be reset for both volatile and non-volatile to 64. Here we go. You see, this is the beauty. So what's the point of this? Why we have volatile, why we have non-volatile? Okay, so let's say now, for example, you are developing a power supply or a sound amplifier. So for sure you don't want like whenever you reset your system, then suddenly your potentiometer set to the and I don't know what limit that might output directly very high output, or they increase the sound to half or more than half. So with this we can preset the power on value using the non-volatile value. So this one, whenever we reset, first it will recall this value, then it will update the what they call the volatile. Then later in the code, if you have any changes, it will follow the changes as well. Okay, so for example, I will demo for you guys something. Let me open the second camera, then we will play with the non-volatile update.
Okay guys, so as you can see here from the camera, whenever I reboot the system, the reading always 2.5 because it's been stored in the system. The non-volatile is 64, which is 2.5. Is same goes if I change it to the other one. There we go, 2.5. Whenever I reset, we'll go to the default value of 2.5. Okay. Hello, 2.5. Yes. Oh, sorry, got some loosey connection here. Here we go. Okay, so I bring it back to the first one. I guess this connection is better. Okay, 2.5. So now guys, if I change let's say I will change this one, I'm connected to the potentiometer 0 to this guy. So if I do the writing and upload, so now we will see that the reading will be changed, but the non-volatile will be maintained. Okay, so the reading will be changed, will be dropped because we set to a higher resistor, so the output will be dropped, I believe. Here we go. You see now here on the CL monitor we set it to 10, and here we go, the reading go down. Okay, now because we already modified, so the volatile is the volatile wiper has already been updated in real time. So now if I change it again to, let's say, 50 or maybe 20 and upload it again, we will see that it will update the reading, which will be increased again by 10 steps, I can say. There we go, it's uploading and done. Reading should be, here we go, 0.8 now. Cool. So now if I close this guy, okay, I commented the write and upload again. So now there is no write, no modification. However, the volatile is still there. Okay, the RAM, we haven't recycled the power on the chip, so the reading will be maintained. Here we go, 0.8. Okay, here we go, it's done, and the reading will be still there because we haven't reset or hard reset the chip. So now when I hard reset the chip, here we go, and because we don't have a write to that volatile, so it will read the non-volatile and update or modify the wiper. So here we go, is 2.5 again. So how to modify the non-volatile? By just writing to non-volatile. So now I will try, so this is to writing to the volatile. Now I will write to the non-volatile. So write to the non-volatile here. I'll try to modify only the first one since we are working on this. So it will be non-volatile. Is it non-volatile? Yep, yeah. So I'll change the non-volatile to 20. Here we go. So I will send to them, send to chip and see how it behaves. Here we go, is writing and done. So if you see, guys, from the serial monitor, it shows that the non-volatile has been updated to 20. Okay, however, the volatile is still 64, and also our reading still 2.5, haven't been decreased yet. Why? Because again, the non-volatile will be updated only if we recycle the chipset. So now I will recycle the chipset. Okay, you notice here, I will recycle the chipset. Then you will see the reading has been updated. Here we go. So you see now the reading is 0.8 volt. Okay, now it's updated. Why? Because I changed the volatile. So with this, I can preset my system to whatever I need. For example, I want to set it to 0. So when I reset my system, it will always go to the minimum output. Okay, without damaging anything before, because you know when you just power up your system, the put of the potentiometer, the put up time will be very faster than the MCU, so that's why it might take some time to control and drive the rest. So here we go, it's 0, but the output still going 0.8, so we need to hard reset the system to get the output updated. Now we can update now we can stop this guy, and we can update our volatile wiper as we wish. For example, I want to send it to 100 now. Can. And this one will be a real time. Whenever let's say after I boot up, I set my output to 0 first, my potentiometer. Then I need to do some process and I can send 100 steps to the potentiometer, which is okay, can. You see now, after it's done, this one directly, boom, is jumped to 4 volts, okay? Because the volatile will be real time, non-volatile only responsible to update the data when it's recycled. And same goes to the what they call the second potentiometer. So I will change, oh sorry, not this one. Oh yeah, it's this one. So it will be non-volatile. I want to change the second potentiometer, okay, to 0 also, or maybe to two steps only. So now we can see that the second potentiometer will be adjusted to 2 steps, the non-volatile one, that it's been recorded inside the memory. Okay, here we go, it's uploaded now. Now we should read it. There we go. Yep. So you see now the non-volatile is 2, however the volatile is still 64 for potentiometer number 1, because again we have been recycled. So if we recycle now, let's connect and connect again. So now both volatile and non-volatile should be equal to 2 for potential number 1. Here we go. Here 1, here 1, and this one we already preset it to 0. However, after we modify it, will take the modified one. Okay, so with this is very important part or function to protect our system from outputting directly a high output. Okay, let's come again. So we have finished with this, I believe. So we read, write, increment, decrement. Volatile also we have read and write into it. However, sorry, this is volatile. The non-volatile, guys, also we read, write, but the increment, decrement doesn't work in here in the high voltage. I don't know. I guess this one is support another chipset, not the one we are working on. So the non-volatile support only read and write, and also for non-volatile wiper 1 also we have played with the read and write, and we learn how to use it. Okay guys, so we have finished with the volatile and non-volatile memory addresses. So now we will talk to the TCON register or the terminal register. So if we search for the TCON in the datasheet to see what it can do, TCON, nope, not this guy, not here. Not this one. This is the status register. I want the TCON. This is it. This is it. So the TCON register is 8 control bits that they control the wipers and the terminals, like every terminal, every individual. Here it is. Okay. So the TCON it's control all these parameters. It's got 8 bits. Okay, this is bit number 0 all the way to 7 and 8, which is 9 bit actually. But this one is how can I say, is reserved and always forced to 1. So our functional one is up to 7, which is 8 bits. Okay, starting from 0. So they are controlling the shutdown of the potentiometer 1, terminal A, potential 1 to connect or disconnected, wiper of potential 1 connect, disconnected. So it's just like connect or disconnect the terminals plus shutdown or enable the put. So what we can do here in our code, I don't want to write anymore to this guy. However, I'll still write, but write to the TCON. It's kind of heavy rain in the background. I'm not sure if you can hear it, guys, but we can still continue. Okay, guys, so we come here to our code again. We don't want to do write. Okay, we don't want to do any of this. Reading, we don't want also. So all this need to be commented. And this one also will be commented. Okay, good. So what we can do, first let's read the default TCON register. So here is the modifying the TCON register. So serial, I can say this is the default TCON register equal to, then I will read the memory address of the TCON register. Yes. There we go. And again, guys, this is a volatile. So whenever we did changes to this TCON register, once we reboot the system, all the changes will be gone and go back to the default. So this is the default. Let's see the default values. Okay, it's done. So let's go to the serial monitor.
Yep, here we go. So the T-con is 245. We don't want to print it in decimal. We want it to be binary, so we can see exactly what happening, which bit is being modified, which pin is not modified. Okay. Okay, it's done uploading. So now we should see the serial monitor. Here we go. And yeah, so we got a bunch of ones, 8 ones. So if we compare that with the data sheet, we can see that here the first one, the first bit or bit number 7 is set to 1. That is not forced to the shutdowns. I mean, yes, we don't have any potentiometer to be shut down. The other one, also 1, is being connected to the resistor. This is the terminal P1 of A, the first potentiometer. Wiper also 1 is all connected. All is 1, all connected and all good because we didn't do any changes. So now, if we want to change, for example, I want to, since my hardware or my multimeter is connected to the potentiometer 0, so I will disconnect the P0, all the P0 terminals. Okay. So what I can do is I can write the modification to the T-con. So this is the default. Then I will try to change it. So I will use MCP right. Yep. Memory address is a T-con register, and the value will be okay, so the value, let me see, since I want to change the last 3, okay, the last 3, so it will be 0B 1 2 3 4 5 6 7 8. Okay, so this one I will target to disconnect these 3 terminals, which is mean I will disable or disconnect all the terminals of potentiometer 0. Okay, let me open the camera. Okay, cool. So guys, so I have noticed actually our potentiometer has been default to 0, because if you notice here, we have set 0 to the potentiometer 0. So let me uncomment this and comment this guy to double check that. So let's see what are the non-volatile for both 0 and boot 1. Non-volatile wiper settings, which I believe is 0, and the other one I guess we set to 2 or 1. We set to 2, yeah. Okay. Okay, now wait for serial monitor. There we go. Yeah, we set it to 0, so that way we can't see any different actually if we apply our new changes. So what I will do is I will set this to the default again to 64, so at least we can see something on the multimeter. So when we disable that potentiometer, we can see the results. Okay. So now I'll send 64. So then we should see, for sure, we shouldn't see anything on the multimeter unless we power up or recycle the chipset. Okay, so it's uploading now, done. Thank you. And again, if you notice the multimeter is still displaying 0, enter. I will repower the chip, disconnect, connect again, and here we go. 2.5 now is good. Now we can continue what we are doing. So here, let's add where here. Yep. So now when we send this, we disable the potentiometer 0, so we should see this value drop to 0 again. Okay, let's see. because we disconnect. Yeah, we disconnect the potentiometer, so it was broken. Oh, yeah. Sorry, this one's calling here. Let's do it again. Okay, it's uploading now. And done, thank you. And here we go. We see now we disconnect all the terminals for potentiometer 0, so the output is 0 now. So what we can do is now I can read the new T-con value. So the new T-con is equal to this guy. So now I can read it again to see what is the new value now. After we modify, but for sure, actually, although we modify again, because this one is a volatile, so it will be updated. So the default and the new one, I don't believe it will be much different. Actually, it should be the same anyway. Okay, so yeah, that's it, or that's all what we can do with the T-con. We can just like how can I say, disconnect specific terminal to help us do whatever we want to do. So yeah, here we go. So the default and the new no much different, because the volatile, it will update whenever we upload the code, unless guys, I guess if I disconnect, okay, I connect again, I believe we can see the difference between the old and new. Maybe, let's see. Yeah, not much difference. Okay, anyway, so now if I don't want to turn off all, I want to turn off or disable only the B terminal. So this is 1, only the B terminal, and B terminal, I guess, is connected to the ground, if I'm not mistaken. Let's see. I guess, yeah, it's connected to the ground. So this connected to the ground will be terminated. So I guess the multimeter should show us 5 volts straightforward. Okay, let's see. Here we go. Yeah, exactly, because terminal B is connected to the ground. We disconnect the ground, so there will be no voltage divider complete circuit, so directly will be taking high side voltage only. And same goes if I disconnect, because this is B. Actually, let me copy paste this for you guys. So this one will be the sequence of the bit as we saw from the data sheet. It will be in this sequence. So okay, so now I'm disconnecting terminal B. Now I will disconnect terminal A. So then I should have 0 volt, because there will be no VCC supplied to the voltage divider. So the output here should be 0 now, because I'm disconnecting terminal A. Yeah, and so on and so forth. The same goes to the terminal, sorry, to the resistors or terminal B, and yep. There we go. Yep, exactly. We got 0 because we disconnect the what we call we disconnect terminal A, which is connected to the VCC or to the 5 volts. So we left only with the wiper directly connect to the ground with a small resistor, which exactly give us 5 volts anyway. Okay, guys, so yeah, that's it what we can do with the T-con. Okay, yep. So now we have finished with the T-con. Now it comes to the what we call status register. So in order to read and play with the status register, I will copy this guy. So this is the status register. So if you notice, guys, the status register we can read only, we cannot modify. Just give a status of the what it's happened in the potentiometer, in the digital potentiometer. So this is, we can say, status register. Okay, and we need to read from the status register memory address. starting blah blah blah. Where's my status register? So I'll read the status register, and that's it. Yep, let's send it to the digital potentiometer. Okay. So while it's compiling, let's search for the status register table, so we can see what we should expect from the status register. Nope. Okay, status register already be printed. Where's the status register data sheet? Why it's hard to be found? Okay, status register. Yeah, here we go. Okay, so our status register shows the first 3 bytes. Oh, sorry, the first 3 bits are zeros, and the rest are 5 ones. Sorry. So from the status register being printed out, we can see the first 3 bits are ones, and the rest are zeros. So if you can see here, this is the status register diagram or table. So we can notice that 8 to 5, we have 3 bits to be reserved and been forced to 1, and exactly what we can see here, and the rest are 0. So let's see what they are mean. So the fourth one, when it's 0, it means EEPROM cycle is not currently occurred. I mean, no writing to the EEPROM, and this is exactly what we're doing. No writing anything, just the EEP, I can say the digital potentiometer just idling, doing nothing, no read, no write. The third bit is when 0 is mean the TCON register network can be modified, which is yes, the wiper and the TCON, yes, it can be modified. We don't lock anything. Bit number 2, when 0, TCON register for network 0, port 0 can be modified, and that's good. Yes, we don't lock anything. And so on. 0 is mean there's no hardware shutdown. Yes, we didn't set, if you remember, in the hardware wiring, we didn't set anything to be shut down. The shutdown just left it open. And the last one, the wiper, 0 is mean memory can be written, the EEPROM memory, which is, yes, we didn't set the write protection. Sorry, this is not the wiper, this is the write protection. If you remember, again, in the hardware wiring, we didn't connect this to anywhere. This means the write protection is not protected. We can access it. So the status, that's it. It just like give us the status of the digital potentiometer. I can't see what is the purpose of that. Maybe just to see the progress or whether if the how can I say, the EEPROM or the digital potentiometer is busy or no. I mean, yeah, it is what it is. Anyway, so now what else left for us, guys? I guess we have come across all of the main functions of the digital potentiometer. Now we left with the EEPROMs. We have about 10, as we said. We have 5 to F, which is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11. Yeah, not 5, sorry, it's 6. 6 to F, which is exactly 10. 10 bytes of EEPROM. So we can just test this 10 bytes of the EEPROM. Then we can move to the second potentiometer, the single, because this one is a dual potentiometer. Now we need to go with the other one to play with what we call the multiplexing SDIO. So now I will read the, let's say, the current EEPROM. Okay. I'm not sure what's inside this EEPROM because it's kind of old chip and from old projects, so might be some data there, but I'm not sure if it will make sense for us or no. Anyway, so if I want to read the current EEPROM, the full length of the EEPROM, which is 10 bytes, so I will have a for loop. So for, let's say, integer address, the integer address will be started from the first address of the EEPROM, which is the first address of the EEPROM, this guy. Okay, so this is where my loop will be started. Okay, and the address will be less or equal to the last EEPROM. Okay, and address will be increased by 1. Here we go. So from here I will print, let's print something here also. So I will have serial.print line, okay, this guy here. Let's say reading the full EEPROM. Okay guys, good. So so we have reached so far that we want to read the EEPROM, the whole cells, as we said earlier. So after we printed the EEPROM address, then we need to, let me copy CL print, so save some time here. So we CL print the address, and since it's work with hex, so it's better to use hex to be printed, then I will bring the close. So we need to close the bracket. Now we need to print the value. So the value of the EEPROM, we need to read it, and I guess this one should be print line to go to a new line. So we need to use MCP read. Yep, and I need to read what the EEPROM addresses. So addresses will be the range from the first and the last. So we just need to follow the address here, and I believe that's it. Let's send it to the target and we see what's the output here. Okay, it's done uploading. Everyone looks happy, and here we go. So why is like this? So I guess this one need to be print line also. Okay, so yeah, we can see some of the cells are 0, some of them I guess 100 something. So I believe this is from my last project data, which is, yeah, not that confidential things anyway. Might be a random data. Here we go. So we start from 6 all the way until F, and some of them 0, some of them go data. So now if I want to change, I can change them, for example, here, or maybe up here, since we read. So now I need to maybe modify or mod the sum of the EEPROM cells. Okay, so for example, I want to write, do MCP write, okay, to EEPROM address. So I want to do, for example, here I have the, what is it, the first, and I'm not sure this one, I guess the 6th and the 10th. So I want to write to the second one, so I will take the first, this is the first address, then I add 1, so this is the second one now. In the second address, then the data I want to write it is, this is 1 byte, is 255, so I want to write 123, for example. Then I want to write, for example, at the last one. Why I always go down? I want to write the how can I say, the second last. So I will take the last value. Oh, sorry, the last value, the last address, the last EEPROM address, and I will -1, so I will go up 1. So this is the last, this is -1, and I will bring 1, 2, 3 also. Okay, whatever. So let's go. And again, guys, this is the EEPROM. We shouldn't put this in the while loop. So we shouldn't put it in the loop function down there. Otherwise, we will be exceeding the cycle of writing in no time. And again, we see here the second one not being printed correctly because we are doing it very fast. We need to add some a breathe time to the chipset to digest the data we give to it. So delay of, let's say, 500 milliseconds will do, and again 500 after finish. So let's check again. Again, guys, it's good to be mentioned here that this is very bad idea to directly write to the EEPROM, where we will really exhaust the EEPROM and we reach to the limit of the life cycle of the EEPROM. So it's the good exercise or practice is to read the EEPROM first. We see if it's matched, then we write only if it's different. This is one I guess I already been explained this idea and also developed the code for this purpose previously, I guess in the EEPROM tutorial. So it's not a good idea to directly write on top of it, although it's the same data. Okay, it's better to read first, check if it's same. We don't need to write back again. Anyway, here we go. Yeah, so now we see have our data been written correctly and we can read it. So I guess that's it for our chip that we use in this part, which is the MCP4241, which is a dual potentiometer. So we have come across and modify all the functions that have been available in the chip. So next, guys, I will move to the second part of this video, where we will talk about 4141 chipset, which is a single potentiometer with multiplex SDIO. Which this is the most important thing, and this is why I have come across this video, or why I have decided to make this video for you guys. So let's continue.